So let's continue with the last talk of the morning session. And so it's a great pleasure to introduce Professor Javier Fernández de Bobadilla, who is talking about Acampo spaces and their applications. Thanks.
Well, thanks for the invitation. So, yeah, I also have to apologize for people that heard this talk or similar talk last year. So the theorems will be the same, but the insights, the conjectures will be a bit different. So last year we had a similar meeting, and thanks to several people in the audience, I had the chance of learning a little bit more in SYC fibrations, and this forced me to think on how to improve or how to modify our construction to cover singular Lagrangian fiber. So we don't have theorems yet, but we have some ideas, and I'll try to be in the spirit of last year and be open with ideas. But the only theorems I will claim in this talk are for the normal crossing situation. So for the toric degenerations and toroidal, we don't have theorems yet. We have some insights and conjecture. So Acampo spaces were introduced in the 70s by Acampo to study the monodromy of the monodromy zeta function of hypersurface singularities. I will not discuss this application here, and they have been revisited by Thomas T.Pelka and myself. So this is my collaborator in all what I am going to say, and now my student Marta Aldasoro has joined the crew in developing Acampo spaces for the toroidal case, and I will say some ideas, but not yet about it. So Acampo spaces have by the moment two applications. One is to produce a monodromy with a special dynamics, symplectic monodromy with a special dynamics. And the other application is to SYC fibrations. I will completely leave aside monodromy with a special dynamics in this talk. So let me straight ahead introduce what is Acampo space without further motivation. So the situation is the following. You consider a simple normal crossing degeneration over a disk. And I will usually write the central fiber. Yeah. So when you have a simple normal crossing degeneration, so the topic of Acampo space is to replace the central fiber by a copy of the Milnor fibration. And you want to do this in a symplectic way. So there is already classical way of replacing the central fiber by a copy of the Milnor fibration, and this is the real oriented blow up of Kato-Nakayama construction. So if you have such a situation, in a punctorial way, you can do the Kato-Nakayama blow up. Let me explain what is the Kato-Nakayama blow up or the real oriented blow up. So real oriented blow up of the disk is to the two polar coordinates. So you replace C by R bigger or equal than 0 times S1. And this means that you create a circle instead of the point. And now when you have a normal crossing divisor, locally, it is a pointed disk times a pointed disk. And this means that locally, you can replace by C log times C log. This I'm going to call C log. And you can glue along chart. So this means that the Kato Nakayama blow up replace these points by S1. And when you are meeting two divisors, this point is replaced by S1 times S1. You know what to do when you have three or more divisors. Okay, so if you have a simple normal crossing degeneration, this map OF log becomes a locally trivial, well, it's a topological submass. So if you are in the proper case, it's a locally trivial fibration. So you already have a radius zero copy of the Milnor fiber. So D log is the disk, and at radius zero you have a copy of the Milnor fibration. So this space is inadequate to do symplectic geometry because it has corners. So we want to smooth the corners in a nice way, in such a way that we can put useful coordinates in it and do symplectic geometry. This is the purpose of a campus space. Okay, so let me, so this is Kato Nakayama construction. So what I am going to do in this talk is to explain in details the constructions for the simple normal crossing case. And I will give some insights for the log geometry case, but in that case, I will assume that you know log geometry. So if you don't know log geometry, just stick to the simple normal crossings. So if you have a log analytic space, there is a way of generalizing the Kato Nakayama construction. Oh, right. This is a functor, but in fact, it is a blow up, and it is the Kato Nakayama blow up.
And one question, how do the MIs enter the table? Is the usually log structures disregard the MI? You will show up with it?
Yeah, you will see.
Project in the level of the ghost sheep says that 1 maps to 1 1 1 solution and 1
Yeah. So now I want to define a campus space. So for this, let me introduce some functions. So a campus space construction starts as follows. So now we consider distance functions are I hat from X to R bigger or equal than 0, equal 0 with the following property. So imagine you have your variety X and you have divisor V1, V2. Okay, so outside the tubular neighborhood of the divisor V1, the function Ri hat assumes the value 1 divided by E. And close to points, the function Ri hat is modulus of set I times a unit. Okay, and set I is a local equation. So they locally look like the modulus of the defining equation, and away they assume maximal value when it occurs. Okay. Now I define Ti hat is -1 divided by Mi log Ri hat. So those that know tropical geometry are recognizing what is going on. Let me define T as -1 divided by log modulus of F. And let me define Wi as T divided by Ti hat. This is Wi hat. And notice that sum from I equal 1 half to n of Wi hat equals 1. Well, equals 1 if x belongs to the divisor. And this may need a little computation, but you will understand very easily. So now let me explain a little bit in an intuitive way what are these functions. So if I have C2 and I have my mapping set 1 times set 2 C, let me write, let me take R1 equal Ri equals modulus of set I. And in fact, to understand these functions, you don't need the angular part. So this is R bigger or equal than 0 to the power 2. And now, if I approach the origin by t to the power W1, t to the power W2 along this line, precisely the Wi functions will take values W1 and W2. Okay, so W1 and W2 measure exponential slope. And this is a generalization for any simple normal crossing degeneration. Okay, so now I want to make a tropical blow up of my manifold X. So I go to Rn and I define some moment map mu coordinates W1 hat, Wn hat. Okay. And I take X times Rn and I take the closure of the curve. Of course, at this point, W1 and W2 are not uniquely determined. So the blow up of this point is by a simplex, is by the simplex W1 plus W2 equal 1, Wi equal balance. Okay. So in this case, what you see here is the origin replaced by a simplex. Okay. This is an inclusion. And now let me define. Actually, you must see this simplex as a piece of the dual complex. So let me recall what is the dual complex. So you put you put a vertex for each divisor di, And if dj meets di, you put an edge. If you have the further divisor and the three divisor meet, then you put a simplex. And the dual complex of the degeneration, so delta of D, is naturally a subcomplex of the simplex with n vertices. So what you are doing in this blow up is to take different phases of the dual complex and copying them on top of different points of X. For example, when D1 meets D2, you put the phase D1, D2 of the dual complex, but if you have three divisors that meet together, then you'd see something like this.
I mean, just a question, this is, you're working with local chart, or local code. Yeah. So how do you do those things when you think code?
I am not working with local coordinates. I define a global distance function.
Okay, then the question,
Oh, you define the global distance function by local coordinates or partition object.
oh, position.
Should I think this is a corner blow up of the corner you have, like this picture? It's the corner blow up of that point in R plus Q, like as Melrose.
I don't know what is a corner blow up, but it
Okay.
looks like so. So, yeah. Good. Now I'm going to define a campus space. So I have X. I have my mapping D. And now let me take X log, D log. And now I have the moment to blow up. And a campus space is just to take the fiber from. So I call this map A. And yeah, this is the definition of, okay, so this, and let me call this pi. This is, this map pi is the Acampo blow up. And there is the following theorem, which is very easy to prove, that Fa is a topological solution. Okay, so I am still at the, so the advantage of all these coordinates will be double. One is that using these coordinates, we will be able to give a smooth structure in a campus space on which we can do symplectic geometry. So we will be able to, if we start by a Keller manifold X, then we will be able to modify the Keller form and endow a campus space with a fiber-wise Keller form. This is one of the advantages. But another advantage is that we have the dual complex of the degeneration built into the space by different pieces. So the different phases, this is a hybrid geometric construction, and the different pieces of the dual complex appear as parts of a campus space. Now I'll be a bit more precise. And it is expected that if you have a maximal Caravilla degeneration, a part of the dual complex, which is the essential skeleton, is the base of the SYC fibration. So I will show at the end of the talk a theorem in that direction. Okay, so a good thing of the campus space is that it has a decomposition. Okay, so X is decomposed as the disunion of xi. Cycle when I is in one n. So for example, X empty is X minus the divisor D, and X I cycle is the intersection with I R Ti minus the union J is not in I. J, okay. And this decomposition passes to the Kato Nakayama space and to the Acampo space. So X log is a union of X log I circle. And what is, so I think maybe we need a name for the Kato Nakayama blow up. So X log I is the preimage. Okay, so if we consider this map is S1 to the power number of I bundle. So this is the torus bundle of the tubular neighborhood. Okay, and now the Acampo space is a decomposition of A X I cycle. Now the good thing is that A X I circle is X, so it has a natural product structure times the simplex delta I, and this is the simplex delta I in the dual complex. So this makes precise, yeah.
I just earlier briefly restate the definition of gamma mu.
Let me, yeah. So let me do it for C3. So I think if I do an example, it will be easier. So okay. So now forget about angular coordinates. So C3. So if you do Kato Nakayama, you would obtain R bigger or equal than 3. R bigger or equal than 0 to the power 3 times S1 to the power 3. That would be Kato Nakayama construction. Let me forget for a moment for the angular part, and let me explain what is the Kato, what is the Acampo blow up in the radial direction.
But isn't that the picture which you had already on the board?
Yeah, but I am explaining it.
Oh, sorry. It's just another space that just is defined locally by replacing
Yeah.
R3 greater than 0 with this other model. Sorry.
Are you fine now?
Sure.
Okay.
I'm actually more worried about the scale down or how to include the things, different corners like the comparisons, family of the K3, right? Which degenerate, say, to like a simplex, like quartex.
I'll do this example in detail.
Okay.
So this is coming next. Okay, so this is a decomposition of a Acampo space, and now I want to show you. Well, you saw tori. So you have this product structure, okay, and now if I do AXI circle, I can send it to XI circle times delta I, and the fibers, this is a locally trivial fibration. Okay, so let me take this. So you see some torus fibers. So this means that if you are in a maximal intersection, you have half dimension tori fiber over a simplex. So if I is maximal intersection, this xi circle becomes a point. This becomes a maximal phase in the dual complex, and now the dimension of the torus is half the dimension of the space. Okay, this is compatible. Actually, this will be SYC tori when we come to the symplectic applications, and I should know when I have to stop.
Well,
15. Okay. Mhm. Let me try to do a couple of examples. So let me start easy by x1 c plus s disk, this maps the disk x. Okay, so the divisor D, maybe we'll call it x0 because it's the zero fiber, is D1 plus D2 plus 3. Okay. And now I'm going to picture the Acampo space at radius C. So I have the Acampo space. And I have the log. And now let me pick a point at the log. And this point is the point 0 theta. Okay, so I have to specify a radius and an angle. I specify the angle theta, and I want to picture AX 0 theta, and AX 0 theta is AX one is union AX 1 2 is union AX 2 AX 2 3 AX 3. So you have 6 pieces, and the Acampo space is a torus that splits in 6 pieces. Well, the fiber of the Acampo space. So let me call this the piece 1, 2. This will be the piece 1, piece 2, piece 2, 3, piece 3, piece 1, 3. Okay, and now everything comes everything is compatible with this construction. So now each of these divisors is a P1, okay? The dual complex is a triangle, okay? So the piece 1, 2 is one of the sides of the triangle multiplied by this one. The piece 2 is a P1 minus 2 points. It's a P1 minus 2 point multiplied by nothing. So it is a cylinder and it glues by the boundary with the interval times S1 and so on and so forth. Okay, so what you see is a copy. You see a copy of the you see a copy of the elliptic curve. So this is the fiber over this point. Now, if I go away, if I take the fiber over this point, I will see an elliptic curve, and as you move from this point to this point, this curve degenerates. Well, it is I told it is a locally trivial fibration, so you have to see nothing, but you have a special decomposition. And okay, so where is the SYC fibration? So we recover part of the SYC fibration from this general picture. In the maximal phases, so the shaded pieces are fiber by S1, okay? And now the non-shaded pieces in this example are toric varieties. So P1 minus 2 point is a toric variety, and this toric variety is fiber by the real torus. So if I consider the real torus, I recover the whole SYC fibration in this example.
But I'm missed a bit. You said it's a disjoint union, so you're not gluing the pieces together.
No, I said it's a disjoint union as a set, but I didn't say that it's a topological disjoint union. As I said, it's a disjoint union. But I didn't say that this is a
I think the picture looked a bit like only 3 cylinders via open.
by
Picture looked a bit like only 3 cylinders via open.
I cannot see what is the reason. But the Ocampo space is connected, so it is connected by definition. So this
So the boundary circle, they belong to 1 or to 1, 2? Which of the
2, 1, 2.
1, 2?
The boundary circle becomes 2, 1, 2. In the 1, you see the open part.
In this picture, we have the Nakayama space contracts the 3 double indexed cylinders
Yes.
to a top of S1.
So US mass on the there. But if you put the Calabi-Yau measure, if you put the Calabi-Yau measure, 100% of the volume is in the 1, 2, 2, 3, 1, 3 part. So when you put the Calabi-Yau form and you compute the volume, most of the fiber goes to the double index part. So this occupies most of the SYC fibration. So in fact, this is the reason why it is expected that the essential skeleton is the base of SYC. Okay, so let me do another example. I think I am very slow and I won't be able to finish my talk, but I think if I discuss examples in a proper way, it will be useful. But already in the curve case, I want to stress something. Imagine that the situation would be like this. 3 elliptic curves meeting the point. Then what Ocampo space would do? Ocampo space would make a little hole here and put this cylinder. Make a little hole here and put the cylinder. Hole here and put the cylinder. And you will see nice S1 fibrations here. But since these are not toric varieties, there is no natural torus vibration on them. So a Campo space produce, so the general Campo space constructions is able to produce SYC fibration over the strata that have a toric structure. And of course, points have a toric structure, which are maximal intersection strata. Okay, this is a little bit the philosophy. And this is a bit the philosophy of this talk, because I promised new insights with respect to last year, and I am going to give some. Okay, so next example. And by the way, already this example is quite rich. This is the dual complex. And in gross Siever language, this is the dual intersection complex. And here you have three toric varieties. And out of the three toric, and by gluing the polytopes of these three projected toric varieties, you can form something grossly in gross Siever language is intersection complex. And now it's a pity that I have spoiled the picture, but I want to still recall that there are some parts that have one color, and the other parts have another color. Okay. So from the viewpoint of a Campo space, what is the base of the SYC fibration? It is not a triangle, it is an hexagon. So what you do is you break the joining in the dual complex, and you interpolate faces of the expanded dual complex. Okay, so so you make a hybrid space by mixing the dual complex and the intersection complex and the section complex, and this we call expanded dual complex. And this is a natural base for the torus fibration. And this can be carried symplectically. Okay, so now I want to show how this yoga applies to the next more difficult example. See. Okay. And now this is a space X. But this space is not smooth. This space has it has 24 singularities that are at the intersection of two coordinate hyperplanes and the zero set of this polynomial. Okay, so nevertheless, I am going to perform the campus. So now I could do two things. So I can play two games. Okay, and this is the game that we play in our joint paper with T.Pelka, is to force to resolve singularity. be. So this is established in a theorem. So so you can resolve singularities by blowing up the hyperplane divisors in the order you want. This produces small resolution. You obtain a smooth space with and central fiber is simple normal crossings, and you can perform a campus space. And this process is not unique. And moreover, you lose the toric structure of the maximal dimension. You lose the toric structure of the maximal dimension components of the central fiber. You don't lose the toric structure of the double intersections. And this is due to a theorem of Minkes, Xu, and Yu. Okay, but I want to explore what would happen if we construct a campus space starting from X. I will comment a little bit more in A later on. Okay, so if you construct a campus space directly from X, so now the dual complex is a tetrahedron. This is dual complex. And now the intersection complex is again a tetrahedron. I won't be able to picture something dual, but I'm doing my best. And now you can construct some sort of hybrid space, and the best way of doing it is to cut a little bit. You first cut the edges. You first cut the vertices, and now you cut a little bit the edges. So this becomes a hexagon. And I hope you see this picture. So it should look like something like this. If you think of a plane. Okay. So you produce some base that is expanded dual complex. So this is a polyhedron, and each of the faces of this polyhedron is the product of one face of the dual complex. So let me, now you have the hybrid picture there. Each of these pictures is a face of the dual complex. Times the dual face of the intersection complex.
Oh, that's not so right. Hexagons are not products, right? Hexagons are not products.
Oh, I see.
The top is the hex.
Yeah, in fact. And in fact, this is probably not a hexagon. This is a triangle. So it's my mistake. It's not a hexagon, it's a triangle. Because the point I replaced by a triangle. And it's this hexagon. So let's see.
You can make it a triangle, but it's very special for the sequence. And you wouldn't be able to do this for other products.
It's because the big triangle should also be a hexagon. Like you replace the vertex.
So
Just when you draw a triangle, it should be hexagon somewhere.
yeah. So they are not products. So
I think in general it's impossible. But for the simplex, yes, you can do it.
Okay, so let me proceed in this example. Okay, so now what you do, you have to. So I want to find another source of tori. So I have a good source of tori over the maximal faces of the intersection complex. Okay, so this, so I have a decomposition of the Acampo space. My Acampo space is decomposed as is written here, and on the maximal faces I have three-dimensional tori. So now let me explain what happens in submaximal faces. So these are the intersections of two coordinate hyperplanes. So for submaximal faces, xi circle is P1 minus 0 infinity, and P1 minus 0 infinity has a canonical fibration to the circle, to the simplex with an S1 fiber. So if I mix with the S1 fibration, that okay, so now in this P1, exactly the meridian, you find 4 special points, which are the special points, which are the intersection of the zero set of this polynomial with the coordinate line. Okay, and in this special point, the Kato Nakayama. So on top of each of these points, the Kato Nakayama blow up would put S1 times S1, but on each of these special points, it just put S1. So this is what the Kato Nakayama blow up does on these points. So this and okay, so this means that you see a torus fibration, but on each of these points, so the torus, you see a torus fibration, and in each of these points, one of the circle gets pinched. So you get 4 fibers over this kind. And now what happens in the maximal dimension, so in the coordinate faces? On the coordinate faces, AX, let's say 1. This is P2 minus coordinate lines. And this is fiber by S1 to the power 2. So topologically, you can find a singular torus fibration with 24 special fibers which are pinched tori. This is what would happen if you do a campus space construction with resolving singularities and you exploit the toric geometry of the strata. Okay, so now I have 15 minutes, and I want to tell a little bit about the smooth structure and symplectic geometry. I took way too much time here, so now I only will be able to state theorems. So this is a theorem for the simple normal crossing case, and I'll state what we expect in general. So there is the smooth atlas in AX such that one AX below is a smooth submersion. I want to introduce some functions. So I want to say how to create coordinates. So I defined the functions di hat. I defined the functions wi hat. Let me define the function eta of s as 1 divided by 1 minus logarithm of s. And let me define vi hat as di hat minus eta wi hat. Okay. All the vi hat are smooth. And the map, a campo blow-up map phi to x is smooth. So this means that you can pull back any differential form in the natural space. Okay, and dCri hat extends to a smooth one form in AX. This will be useful to put angular forms. And why? I think this is more than okay. So we have a smooth structure in the Campo space like that. And now let me state a conjecture. So now let me take f x mx to d. And now you put the divisorial of a structure associated to 0. So if this map is exact log smooth, then applying a Campo space to the log geometry situation, you still get a smooth submersion. And similar theorem. Okay, so now I want to say what is the theorem about symplectic structure. So I say fiber-wise scalar, but fiber-wise scalar, this is any radius. And this is a positive radius. And this is a theorem, and this for the simple normal crossing situation. And I will cheat a little bit, give a slightly simplified version of the theorem. There exists a potential phi in x minus b are bigger or equal than 0, such that t times phi extends to a smooth function in AX. Okay. D D C phi extends to a smooth 1/4 X C for all epsilon positive small enough. Pi upper star omega x plus epsilon d d c phi is fiber-wise symplectic, and the all tori appearing in the torus fibrations coming from Kato Nakayama blow up are isotropic. Okay. So this creates torus Lagrangian fibration in the over maximal phases, and if you consider this example, you can prove that the tori appearing in the P1 minus 2 points are also isotropic. So let me state the part E, and here I assume X D maximal Calabi-Yau, and I assume Nikkei's Su U model. Nikkei's Su U model means that if I have xi circle is C star or I equal n minus 1. Okay. So if I have then we have S1 to the power n Lagrangian vibration in the submaximal locus expanded dual complex. So I am stating this fast because I have to finish in a minute, but now I am going to explain what is expanded dual complex in general. So dual complex looks like this. Expanded dual complex in general, you don't care what happens about. So only when you have submaximal intersection, you replace via connecting. So you replace delta I time by an interval when I is submaximal. Okay, so I think this is the time I have to